Hello, welcome to our review lesson for trigonometry required for calculus. As you can see on your notes sheet, or you could just follow along even if you don't have a notes sheet with you, it says a course with trigonometry is a prerequisite for calculus. That means you're supposed to already know it. Trigonometry is sprinkled throughout calculus. I put that in there just so you know that it's not as if the trig is going to come up at the start and then go away. Neither is it the case that there's just a big block of calculus that uses trigonometry. It very much comes up just here and there throughout the entire class. And so the facts that we're about to review are content that you need to get into your long-term memory if they aren't there already. So just as a quick starter out, we're going to talk about the fact that we label a right triangle, as you see right here. This is our SOHCAHTOA idea. If you know that mnemonic device, that helps you to remember the principal trig relationship. It's sine, cosine, and tangent. And those are listed right here in this part. And then the reciprocal relationships are listed next to it. So, for example, sine and cosecant are reciprocals of each other, as you can see by the fact that you flip this fraction over here. Okay, so that's just a little reminder about SOHCAHTOA. That is where trig comes from. It's from that triangle. But then we start thinking about, well, what if we wanted to look at an angle theta that didn't fit into a right triangle? In other words, it's not an acute angle. So if we look at angles that are larger, we need to think of those angles as angles of rotation because they don't fit into a right triangle. Like if this angle theta here was like 120 degrees or something, that can't be in the triangle because it would violate the rule that triangles can only add up to 180 degrees. It is not physically possible. I shouldn't say it like it violates a rule. It actually isn't physically possible. That's why it doesn't happen. So if we think of angles that are above 90 degrees and think of them as angles of rotation, then we can think about their corresponding reference triangle. That's the part I'm highlighting in green right now. And within that reference triangle, you can call the horizontal component X and the vertical component Y, and then label the hypotenuse R. We use R because it's the radius of a circle, the circle of rotation that we're looking at here, and then you get these definitions. Now, these are exactly the same as what you have over here relative to that green reference triangle. Now, the reason it is so helpful to have that R labeled as radius is because then we make the cosmic leap in a trig class of letting the radius equal 1 in a circle that has radius 1. That's called the unit circle. And that would mean that this R and this R and this R and this R are all 1. But in particular, the part that's of interest to us is the fact that cosine then would equal the x, or the horizontal component, and sine would equal y, or the vertical component, when r is equal to 1. So that's of interest because that really builds the unit circle for us. And so if you flip ahead, here's a picture of the unit circle. And all of these values come from that reference triangle we were just talking about. For example, this is a reference triangle with a 30-degree angle right here. If this is 1, the short leg would be half of that, and the longer leg would be the short leg times radical 3. Well, that's how you get those coordinates right there, okay? So it's not hopefully mysterious where this comes from, but this unit circle certainly is something that you should be very familiar with, very able to recall values from. These are some of the identities. The reciprocal identities I mentioned early on when we were looking at the SOHCAHTOA definitions back here. But these are the functions that are reciprocals of each other. You certainly should know that tangent is sine over cosine, and it follows from that that its reciprocal would be cosine over sine. These certainly come up in a trig class, the Pythagorean identities. Honestly, after a long summer, I know I even have a hard time sometimes remembering for the second and the third one, which side has the 1 or which one is what. I know that sometimes I'll have to remind myself, okay, well, I know sine squared plus cosine squared is 1. I'll start out with that fact. And then if you imagine dividing through, say, by sine squared, like this, then you end up with this first fraction giving you a 1, the second fraction giving you the cotangent squared, and this last guy is cosecant squared. And look at that. That is this guy down here. How do you figure you get that middle one? So you start with sine squared plus cosine squared equals 1 again. So you really have to know that first one. But if instead of dividing through by sine squared down here, you take all of these and make cosine squareds, then you derive this guy, okay? The second Pythagorean identity on that list, okay? So really, you can figure out the other two when you need them, but you really have to at least know one of them in order to derive the other two, okay? I would recommend knowing sine squared plus cosine squared equals 1. Double angle identities, I debated whether or not to put this on here, but I do remember there is a homework problem somewhere along the line where this is useful. I remember arguing with my class before, my previous class, about how could they possibly be expected to know that. I just think you could because it was in your class last year. So, but that's the double angle identity for sine. I don't actually remember the others coming up for sure, if they did or not, but I know that that first one did in a homework problem. Even and odd identities, these I think you really should be able to think about if you think about the graphs of the function. So let's flip to the graphs for a second. When I look at the graph of cosine, for instance, here's my sinusoidal curve that we call cosine. And cosine goes through the point 0, 1. And I can see that it is symmetric here on either side of the y-axis. And so that kind of symmetry is what we refer to as reflective symmetry across the y-axis. It's also indicative of an even function. Now let's look back here. Cosine, if you look right here, it says cosine of negative theta is the same as cosine of positive theta. Look at that graph. Pretend this is some positive theta. The opposite of theta would be right here. Don't those have the same function values? They're right across from each other, right? See, it makes sense. Okay, so that's really all that's saying. With sine, it's not quite the same. It says sine of negative theta equals the opposite of sine of theta. Well, let's look at our graphs, okay? I'm going to use a different color now. Over here, here's my sine curve. Let's call this some amount theta. Over here, I'd have, that same amount to the left of the origin. My values are opposites, right? This is a positive value over here. This is a negative value over here. They're the same amount up on the right as down on the left, but they are opposites of each other. That's exactly what this statement says, right? Whatever value you get at negative theta on the sine curve is the opposite of what you get for the sine of positive theta. So these even and odd identities, think about the graph. Think about the graph of the function, okay? If you notice here, cosine and secant are what we call even functions. They have that nice symmetry with the y-axis. None of the others have that. The rest of them are all what we would call odd functions. Now, functions don't have to be either even or odd, but in the case of these trig functions, they are. They either are even or odd. None of them is what we would call neither, okay? Odd functions have that opposite effect, okay? Where you go up on the right, you go down on the left. You can see this, or vice versa. So you can see this in tangent, right? Wherever, if I pick this as my spot, I go up a certain amount. The opposite input value gives me the negative of that amount, okay? There's rotational symmetry, we would say. There's rotational symmetry around the origin. That's what an odd function has, okay? I'd also just ask you to study these graphs. You should be familiar with the fact that sine and cosine are the graphs that give you these waves. You should know that sine goes through the origin. You should know that cosine does not. Cosine starts on a hill, so to speak. You should know that tangent is down on the left, up on the right for each of these branches. You should know that the width of these asymptotes is pi. They are pi units apart. The period is pi. That fact is right up here, okay? You should know that in contrast, tangent and cotangent, this guy goes the other direction, up on the left, down on the right. You know that it has an asymptote. Cotangent has an asymptote here, whereas tangent goes through the origin, okay? And these other two graphs aren't maybe as frequently used within the calculus context, but you should be familiar with them as well. Cosecant is the reciprocal of sine. So if I were to draw a sine curve in here, it would go like this. And at the hills and the valleys of the sine function, you get the smiley face and frowny face of the cosecant function. Same thing over here. Secant and cosine are reciprocal. So if I were to draw the cosine function in here, it would be right in here like that. And wherever there's a hill on the cosine function, you have this arc that goes like this. And whenever there's a valley in the cosine function, you'd have a frowny face kind of shape like that. Okay? I hope this has helped brush off the summer cobwebs, and feel free to watch this as many times as you like. Ask me questions in class, or ask me for some more review material, and I can find you some things that will help you feel very confident and comfortable with your trig.